what we were doing, let's scroll too far, is starting to work on this problem where we had repeated complex poles. No, I don't want to go to tablet mode. Yes, I probably need to actually look at notes here. All right, so we had used our good old 8th grade math quadratic equation to figure out what the poles of this second order polynomial s squared plus 10s plus 34 was. We found the poles to be -5 plus or minus j3. And so that allowed us to write this polynomial as s plus 5 minus j3 quantity squared times s plus 5 plus j3 quantity squared. So we see that we have a very similar situation to the last example that we worked, except that now we have a repeated complex pole, or actually we have 2 repeated complex poles. So the expectation here is that we're going to have 2 coefficients, 2 expansion coefficients, B1 and B2, and we're also going to have the complex conjugate of those expansion coefficients as well. So realistically, we should expect this thing, our equation f of s, to be of the form B1, which will be a complex number, or maybe a complex number, over s plus 5 minus j3 plus B1 conjugate over s plus 5 plus j3 plus B2 over s plus 5 minus j3 quantity squared plus B2 conjugate over s plus 5 plus j3 quantity squared. And because we have repeated poles, even though they are complex, we're going to wind up using our method for the case of repeated real poles. So our coefficient B2, let me get rid of this thing. Is going to be determined by multiplying our equation f of s by a factor of s plus 5 minus j3 quantity squared, evaluated at s is equal to -5 plus j3. And so expanding this thing out, we're going to have s plus 5 minus j3 quantity squared times 108 times s squared plus 2, all divided by s plus 5 minus j3 quantity squared times s plus 5 plus j3 quantity squared, evaluated at s is equal to -5 plus j3. This guy cancels this guy. And we wind up getting 104.957 with an angle of 120.964 degrees. So I'm choosing the S value that makes this part right here go to 0. So that's why I need a negative real part to cancel out this positive 5, and I need a positive imaginary part to cancel out this negative J3. Good question. So our coefficient B2 conjugate is literally just going to be 104.957 angle negative 120.964 degrees. To calculate B1, we are going to take the first derivative with respect to S of S plus 5 minus J3 quantity squared times f of S, and then evaluate this derivative at S is equal to negative 5 plus J3. So that would be the derivative of this part right here that's left over. I'm going to pull the 108 out because it'll make our life a little bit easier. So that's going to look like, actually, this is big and ugly. So let me do it down here. 108 times, and now I'm going to do the quotient rule. And I think I'm about to sneeze as well, so I pre-apologize. Nope, okay. I'm sorry about that. So we're going to have, let me scroll up here so we can see it, right? So the rule here with the 108 taken out is we're going to have our denominator times the derivative of the numerator function minus the numerator function times the derivative of the denominator function divided by the denominator squared. Okay, so that's going to look like S plus 5 plus J3 quantity squared times 2S minus 2 times S plus 5 plus J3 times S squared plus 2. Yeah. All of this divided by S plus 5 plus J3 to the 4th power, evaluated at S is equal to negative 5 plus J3. And I wound up getting 36 angle negative 90 degrees here. So one thing that I do want to point out, I actually worked all of this junk out by hand. And when I was trying to do this calculation in my calculator, it had a mild panic attack. It kept giving me domain errors. And I figured out that the reason it was giving me a domain error is because it really doesn't like anything higher than squaring a complex number. Okay. So to do this part here, I had to do it as, substituting this value in for S squared and then squaring that result, because if I tried to do it to the 4th power, my calculator just crapped itself. So just wanted to give you guys a hint. I did not check to see whether MathCAD could just do it from the jump. My best guess is it could, but when I was doing this by hand at my kitchen table, or by hand with a peasant calculator instead of my computer, it did give me a problem. So I just wanted to make you aware of that problem in case you face it as well. So I got around the limitations of my calculator by treating that as this quantity squared and then squaring that result, which should be the exact same thing as the 4th power. Okay. Then we have B1 conjugate, which is just going to be 36 angle positive 90 degrees, because that's how the conjugate operation works. And from this, we find that f of S will be 36 angle negative 90 degrees divided by S plus 5 minus J3 plus 36 angle positive 90 degrees divided by S plus 5 plus J3 plus 104.957 angle positive 120.964 degrees divided by S plus 5 plus J3 quantity squared plus 104.957 angle negative 120.964 degrees divided by S plus 5 minus, actually, my apologies. This should be the minus sign right here, positive sign over here. My mistake. So, technically, we already know how to do the inverse Laplace transform of these first two terms. That's the last thing we did, right? So we can very easily see that this is just 36 times one, e to the j negative 90 degrees over here, e to the j positive 90 degrees over here. And then we have those complex roots. So that part of things is going to look like 72 e to the minus 5t cosine 3t minus 90 degrees u of t. So that's the part that comes from these first two terms, applying the relationship that we effectively derived at the end of our last class week. And now we have this big ugly guy up here, right? So this is going to look like 104.957 e to the j 120.964 degrees times t e to the negative 5 minus j3 t u of t. And because I'm running out of room, I'm going to continue this on down here. We'll have 104.957 e to the negative j 120.964 degrees times t e to the j, sorry, no, negative this should be 5 plus j3 t. And I'm realizing that this 5 looks too much like an s, so I'm rewriting it to be more obvious. U, come on, stylus, there we go. U of t. So effectively, if we kind of get rid of this complex number up here, this looks like something of the form of 1 over s plus a quantity squared for both of these, and that would be t e to the negative 8t, where the a is 5 plus j3 for this guy right here, and 5 minus j3 for this guy right here. So it should come as no surprise to any of you that we can play around with the exponentials and cram these things together into a single waveform. Yes, Lucas.
Yes, I'll see why logarithm on the outside of it. And I thought it was good taking the log of it.
There is no logarithm whatsoever. That number is 108.
Oh.
So sorry for my bad penmanship. There was no log at all. That was just the number 108 multiplied by things. So I took that out because that is a constant term. If it were a logarithm, it very much would not be. So, nope, sorry for my bad penmanship. Any other questions before we smash these things together? Scroll down a little bit, okay. So, excuse me. What we're gonna do now is we're effectively gonna do the exact same thing we did when we first saw complex conjugate roots, right? So I can see very easily here that I'm gonna have this number times t e to the negative 5t, that same number times t e to the negative 5t, that part's gonna come out. So 72 e to the negative 5t cosine 3t minus 90 degrees u of t. I'm going to put it down here so that I have plenty of room. 104.957 t e to the minus 5t. Then I'm going to have, let's see, so this first term, I'm going to have e to the positive j, because negative j is positive j. 3t plus 120.964 degrees plus e to the negative j, 3t plus 120.964 degrees. Close all this, use a step function. And then I know that this plus this is literally just twice cosine the argument of the exponential function, giving me finally 72 e to the minus 5t cosine 3t minus 90 degrees plus 104. Actually, sorry, that 104 should be multiplied by a factor of 2. 209.914. T e to the minus 5t cosine 3t plus 120.964 degrees. All of this multiplied by a unit separator. So we have covered practically every case that we could. Technically speaking, we can actually now have some relationship for when we have a complex number over a repeated conjugate root. I did not do second derivative, third derivative type things because just the math there is just ridiculous. I didn't want to do it, so I'm just going to hit you with the identity and take it for what it's worth. So when f of t is equal to t to the n minus 1 divided by n minus 1 factorial, which in our case, n was 2, so that's literally t to the 1 over 1. E to the negative at cosine omega t plus some phase angle. The Laplace transform is f of s is equal to 1/2 times e to the j theta over s plus a minus j omega to the nth power plus e to the negative j theta over s plus a plus j omega to the nth power. And 99 times out of 100, we're actually going to use it to go from the s domain back to the time domain as opposed to the other way around. So that's now the last identity that you could possibly have to use for any type of signal we can be able to realize. Grayson. n minus 1. So it's whatever number of repeated roots we have. So for our example, we had doubly repeated roots, so n was equal to 2, which is why we wound up having t to the first power divided by 1 factorial, which is just t. E to the negative at, where a was the 5, the real part, and then our phase angle theta was this 120 business right here, and omega is the imaginary part. This guy right here. Yes, Ryder. Sure. So let me write this down in blue, right? So we have a function whose S domain representation is some complex number divided by S plus A minus J omega plus E to the negative J theta over S plus A plus J omega. Our thing is in that form, except that we happen to have a factor of 36 floating around in there as well. In the time domain, this looks like e to the negative at cosine omega t plus b. So I was able to identify my a as 5. My omega was 3. Theta was negative 90 degrees, if I'm remembering correctly. And because I have a factor of 1/2 over here, I need to effectively double it to get the right number in the time domain. Right, so if I had 36, I double it to get 72. Just like here, I had 104.957, multiplying it by this thing, which is equal to twice cosine, is what forces me to double that number to get the double it to get the right number in the time domain. Any other questions about this horrifyingly ugly thing? All right, so we have spent the better part of 2 weeks, possibly over 2 weeks, just doing a crap ton of math. This is circuits 3. So now let's see how all of this crap deals with circuits. So my goal today, and we only have about 30 to 45 minutes left, is to help provide some context, and then we'll get into more nitty-gritty details in our later class meetings and all that kind of stuff. So the first thing that I want to do today is I want to look at what the S domain representation of circuit elements are going to look like. Because effectively what we're going to be doing is very similar to the analysis that we were doing in the frequency domain previously, except now we're going to explicitly be working in the S domain, and the rules are similar, but they're slightly different, okay? So let's take into account, let's see, grab my notes here. If I have a resistor, actually, let me title this circuit analysis in the S domain. So if I have a resistor, we know that in the time domain, our voltage V of t is simply equal to R times I. This is just good old Ohm's law, right? What is this going to look like in the S domain? Well, I'm going to take the Laplace transform of this thing, right? So the Laplace transform of V of t must be equal to the Laplace transform of R times I of t. R is a constant value, so I'm just scaling that thing, right? So the Laplace transform of V of t will be just V of S. That will be equal to R times the Laplace transform of I of t, which is just I of S. So effectively, once again, Ohm's law is Ohm's law, regardless of the domain we're working in. I know it's absolutely mind-blowing stuff, but we need to have something to point back at, right? So Ohm's law works the exact same way. That's great, right? If we wanted to define, I hesitate to call it an impedance because we're not explicitly working in the frequency domain here. We're working in the S domain. It would still be the ratio of the S domain voltage divided by the S domain current, which means resistors look like resistors everywhere. Now, let's say, actually, let me do a very simple and dumb demonstration here. So in the time domain, just because I'm going to put pictures up for the other things as well. So in the time domain, we have V of t is equal to R times I of t. This is R. Let's say that our voltage V of t is like so, and our current I of t is like so. In the S domain, we would have R. Our voltage drop would be V of S. Our current would be I of S. And we would have V of S is equal to R times I of S. And this is our S domain representation. All right, so now for some inductor L. Mathematically, our time domain representation is V is equal to L di by dt, right? So what's this going to look like in the Laplace domain or in the S domain? So I'll have the Laplace transform of V of t must be equal to the Laplace transform of L times di by dt. So on the left-hand side, we are just going to have V as a function of S. What does taking the derivative in the time domain look like in the S domain? You guys have a table with properties. Look at your table. What does it entail? So we're doing a first derivative. So just S. So multiplying by S. But we're also going to have a term that's dealing with the initial conditions. Right? So if you look at your table for the derivative, there's that. So in this case, n is 1. So we'll have f of 0 minus or whatever, right? That we're going to have to deal with. So what we are going to have is L multiplied by S times I of S minus I at 0 minus, or SL times I of S minus L times I of 0 minus. So this is our mathematical relationship. Now let's describe, you raising your hand? That's exactly right. So that is a time domain relationship, which is why I'm using the lowercase I. So the capital letters here are our S domain quantities. Lowercase is our time domain quantities. So the representation of an inductor in the S domain depends on what current was flowing through the inductor in the time domain at t is equal to 0 minus. Absolutely right. So once again, I think a picture will kind of help describe what's going on here. If we had an inductor in the time domain whose value was L, we would have the voltage drop V of t, the current I of t, and the relationship V is equal to L di by dt. In the S domain, we'll have our inductance, and it'll have, I hesitate to call it an impedance, but it's effectively an impedance, SL. And then we're also going to have that in series with a voltage source, which is taking care of the initial condition part, where the value of that voltage source is L times I at 0 minus. The S domain voltage for our element is the voltage drop across the inductor impedance and that voltage source. And our S domain current is the current that's flowing through the inductor into the negative polarity terminal of this source that's taking into account the initial condition. Where we could say that V of S is equal to SL I of S minus L I at 0 minus. And because I have a voltage source in series with an impedance, I can actually do a source transformation on this thing as well. So if I wanted to view it from the perspective of an inductor in parallel with a current source, I would have the following relationship. Right? So this is still going to be SL. This is going to be my voltage drop V of S. Here's where my current I of S is defined. And the value of this current source will be there's going to be I at 0 minus. Keep wanting to use subscripts, but I haven't been consistent with it. Divided by S. Where we could say our current I of S is equal to V of S divided by SL plus I at 0 minus divided by S. Both of these are S domain relationships. So we can use whichever form will make our circuit analysis easier, right? If it helps to have a voltage source in series, we would use the one on the left. If it would help to have a current source in parallel, we'll use the one on the right. I'm going to get the same answer either way because they're source transformations of each other. They are the exact same, or they are electrically equivalent. I guess would be a better way to say that. Now, let's look at capacitors. Sorry. For a capacitor C, we know that I of t is equal to C times dV by dt. So the Laplace transform of I of t will be equal to the Laplace transform of C times the derivative of the voltage with respect to time. So this is going to look like I of S is equal to C times S V of S minus V at 0 minus. Okay. Should literally be the exact same relationship that we had for our inductor, except that we're replacing I with V and we're replacing L with C. So let me scroll up here to make sure I didn't goof that up. Nope. Expanding things out, we have SC V of S minus C times 0 minus. So our graphical representation of what's going on the left, I'll have my time domain again, where we have our capacitor C, our voltage in the time domain, current in the time domain, and we have the relationship I is equal to C dV by dt. And the frequency domain, this is going to look like a capacitor in parallel with a current source. So we'll have 1 over SC here. This will be our voltage V of S. This is our current that is equal to C V at 0 minus. Here is our current I of S. And again, this relationship simply I of S is equal to SC V minus C V naught. And doing a source transformation on this thing, we can put it as a capacitor in series with a voltage source. So there's our capacitor and its impedance, 1 over SC. Here is our voltage source, V at 0 minus divided by S. The voltage drop across this whole thing is V of S, and the current flowing down is I of S. And let me see if I did it up here. Yeah, I did. Okay. And the other, sorry for scrolling so quickly, that was a mistake. V of S in this case would be the voltage drop across our impedance. So that's going to look like IC, that's going to be I of S divided by SC plus V at 0 minus divided by S. So once again, very, very similar to what we saw in the frequency domain, but we actually have our initial conditions on our system built into our analysis. Sure. Absolutely. So if we look at things here for the inductor in particular, right? So L times I, everything is based off of the direction of our current in the time domain and the polarity of our voltage in the time domain. When we move into the S domain, we should see that our S domain current is in the same direction as our time domain current, and our S domain voltage has the same polarity as our time domain voltage, right? So when we apply that time differentiation rule, we wind up getting a minus sign here, which means the polarity of this voltage source has to be the opposite polarity of the overall voltage across the thing. And then when we do the source transformation, because the positive polarity is on bottom, we have the current direction down. So a similar thing is going on here, right? So this IS is effectively splitting up between two paths because this current is in the opposite direction, or because we need a negative sign, we need this current to be flowing in the opposite direction as IS. And then when we do our source transformation, because the arrow is pointing up, the positive polarity terminal is on top. So it definitely seems weird, but there is a rhyme and reason behind why it works that way. Okay, so now that we know what resistors, capacitors, and inductors look like in the S domain, let's look at a circuit. And what I want us to do here, I want us to look at a circuit that we solved way back in circuits 2. We're going to work a transient analysis problem from circuits 2 in the S domain and see if the answers that we get are similar. Okay, so here's the example that I want us to look at. Okay. Let's say that we have a current source, and it is a current that is 5 U of t amps, which means with 0 amps all the way up until t is equal to 0 minus, and then it started sourcing 5 amps for the remainder of the circuit. And I just want this connected to a simple parallel RLC circuit because I don't want this to take forever. Let's make up some numbers. Hit me with a reasonable-ish result. 10, okay. What should the value of my inductance be? 2. Let's keep it reasonable-ish. What about my capacity? 0.5. You guys are using just weird numbers. All right. So this is our circuit in the time domain. And just to make our life easier, we're going to solve for this voltage because I want to solve it like we were solving it as a circuit 2 problem and then verify that we get literally the exact same result analyzing the circuit in the estimate. Okay. So this is a parallel RLC circuit, and it is a parallel RLC circuit where our initial conditions are effectively 0, right? Because there is no current flowing through the circuit before time t is equal to 0. So there shouldn't be any energy swing. For a parallel RLC circuit, what should alpha be? Some of you guys had this like literally less than 2 months ago. Just throwing that out there. I believe it's 1 over twice RC for a parallel RLC circuit. Right? So what's that come out to? 1 over 10. What's omega naught? 1 over root LC. What's that going to be? Saying 1, 2 times a half, so 1 over the square root of 1. Yeah, that's definitely 1. All right. Putting this together, what are we expecting the response of this circuit to look like? Omega naught is greater than alpha, so this would be an underdamped circuit, right? And because we have an underdamped circuit, we are going to have some frequency omega d that we're going to be dealing with, where that omega d is going to be the square root of omega naught squared minus alpha squared. So I'm just going to throw that in my calculator real quick. I don't need a cube root, I'm going to square root. 1 minus 0.1 square root of that whole thing. 3 square root of 11 over 10. Or in normal people numbers, 0.995 after a little bit of rounding. Okay. So by inspection here, let's see, what pieces of information, if we were solving this circuits 2 style, what pieces of information would we need, right? We need the voltage drop, we need the current flowing through the capacitor, and we need the current flowing through the inductor, right? So I'm just going to go ahead and label this guy IL, label this guy IC. At t is equal to 0 minus, our source just looks like an open circuit. Our inductor looks like a short circuit. Our capacitor looks like an open circuit. Here's V of 0 minus, IC of 0 minus, IL of 0 minus, and all these are 0. Right? There's no source in the circuit, so why would there be any of that stuff? Okay. At t is equal to 0 plus. Now our 5 amp source is actually going to be connected. Our resistor is still going to look like a resistor. Sorry, that should be 10 ohms. Our inductor will have the exact same amount of current flowing through it at t is equal to 0 plus as it had at t is equal to 0 minus. Since that was 0, our inductor is going to look like an open circuit. Over which we'll be measuring the voltage V of 0 plus. And here is our inductor current IL at 0 plus. Our capacitor is going to, since its voltage cannot change abruptly, since the capacitor voltage was 0, it has to remain 0, which means our capacitor is now going to look like a short circuit. Here is our current IC at 0 plus, and we can see that, let's see, so IL at 0 plus is still 0 amps. V at 0 plus is still 0 volts. IC at 0 plus is now 5 amps. Everybody on board with that? Okay. At T is equal to infinity. We have our 5 amp source connected to our 10 ohm resistor. Now we're at DC steady state again, so our inductor is going to look like a short. Our capacitor is going to look like an open. IC at infinity. V at infinity. IL at infinity. By inspection, we know that IC at infinity is 0 amps. V at infinity is 0 volts. IL at infinity is 5 amps. Right. Now we would put all this crap together and figure out what our response equation would look like. Once again, we're trying to find V of T, right? So because this is a underdamped circuit, V of T should be of the form. Let's see, if I'm not mistaken, it will be B1 cosine omega dt plus B2 sine omega dt e to the negative alpha t plus d at infinity. Does this look right? It's been 6 months since I taught this. All right. So at t is equal to 0 plus, we are going to have B1 plus V at infinity. Since V at infinity was 0, V at 0 plus is B1. B1 is equal to 0 volts. That seem right? So at T is equal to 0, cosine goes to 1, sine goes to 0, so this whole time goes away, e to the 0 is 1, so all we're left with is B1 plus this term out here will be constant. Based on this, that 0, V at 0 plus was also 0, so 0 equals V1 plus 0. The only way that works is if V1 is 0. Then we have our inductor, or excuse me, capacitor current relationship. So we would have IC is equal to C dV by dt. Oh geez, I have to remember this off the top of my head. Omega d B2 minus alpha B1 cosine omega dt minus omega d B1 plus alpha B2 sine omega dt e to the negative alpha t. Let me pull up my table just to make sure I'm not swapping up those. That's what you have in your notes? Okay, then, well, but no offense, I know who taught you. Okay. No, I mean, I wasn't trying to be more of a jerk than usual, but yeah. All right. If that's what is in my videos, then let's assume that it's right. So yeah, what an ass I am. So at t is equal to 0 plus, oh, and I forgot no, that's right. Actually, no, I did forget that. I should have a C there. So this is going to look like C times omega d B2 minus alpha B1. let's see, we know that B1 was 0, so this whole term right here goes away. So this looks like 5 amps is equal to 0.5 farads times omega D, which was 0.995 radians per second, times B2. So B2 should be approximately, so let's see. 5 divided by 0.5 times my previous answer, 10.0504, something like that. Yeah. For volts. And putting these things together, our voltage V of t would then be 10.0504 sine 0.995 t e to the negative 0.1 t volts. All right. So that's the result we got working this out using our simple second order circuit analysis techniques that we developed in my previous classes. Now let's look at this thing in the S domain. Okay. So in the S domain, we're going to have our current IS as a function of S, and we'll do the Laplace transform of that in a little bit. It's a step function, so it should literally just be 5 over S, but we'll get there in a moment. Our resistor is 10 ohms. Since our initial conditions on this system were 0, that voltage source is going to look like a short circuit. So that's why I'm not including the voltage source here. So we're just going to have an impedance that is S2. Or actually, let's put it as 2S because that's going to confuse me. And then over here, our capacitor is going to have an impedance of, let's see, 1 over SC. So 1 over 0.5 is going to look like 2 over S. And we're trying to find V of S. So just to make myself a couple of notes here, because I am very bad at using numbers, this is R, this is just S times L, and this is 1 over S times C. So I would say that V of S should just be IS times 1 over R plus 1 over SL plus SC, like so, where I'm just treating those as 3 impedances in parallel and combining them in parallel to use Ohm's law to say that the voltage is the current times the equivalent impedance of those two. All right. Let's do a little bit of math here, or not really math, it's algebra to make things look prettier. So I'm going to multiply by R S times L times R in the numerator and the denominator to get rid of some of these ugly looking fractions. All right. So that's going to give me I as a function of S times, I will have S R L in my numerator, SL plus R plus S squared RLC. Does that look okay? Anybody have any problems with my algebra there? What's the Laplace transform of the unit step function? You have a table. 1 over S. So we have Vs is equal to 5 over S times, so let's see, what's R times L? 10 times 2 is 20. So 20S. LS is just 2. So 2S plus 10. What's R times L times C? So 10 times 2 times a half. So 10 times 1 is 10. 10S squared. All right. I feel pretty strongly that we know how to do the inverse Laplace transform of this, right? Because I have one distinct pole, and then this is going to give me complex conjugate poles based on how this thing looks. Right? So let's think about things. This is going to be of the form A1 over S plus B1 over something we'll need to figure out in a moment plus B1 conjugate over that other thing. I think this is going to be the way. Yes. Sure. Why not? That will get rid of this guy right here, which if I had left it that way, I'd be willing to bet that my A1 coefficient was going to come out to be exactly 0 because I don't have a constant term in what I saw in my time domain relationship. But yes, we could do that. So getting rid of this over here. So this just looks like 100 over 10S squared plus 2S plus 10, right? So what are the roots of this thing? So I'm going to have -2 plus or minus the square root of 4 minus 4 times A times C. So that looks like 400. So 4 times 10 times 10 is 400. Divided by 2A. So 2 times A is 20. So let's see. So -2 over 20 is -0.1. And then the square root of 4 minus 400. Actually, square root of 400 minus 4 divided by 20 is plus or minus J 3 square root 11 over 10. Do those numbers look familiar? That's alpha and that's omega naught, or omega D, actually. Right? Or was it omega naught? I think it was omega, no, it was omega D. Omega D, here I calculated it as the square root of omega naught squared minus alpha squared. Let me write that down for you. So where was I going? We'll finish this up on Friday because we only have like 2 minutes left. But effectively, you should be seeing things starting to move towards exactly what we saw in the time domain. That's, the analysis is arguably a lot easier.